In this video, we're going to connect f, f prime, and f double prime. Being able to analyze and see the connections between these graphs is an important skill to master, and it's one of the most heavily tested topics on the AP exam. It can be applied in many different situations. In addition to the things we've already learned, here are some other important things to know before we can start analyzing the graphs of f, f prime, and f double prime. The first derivative test for local extrema. There is a local minimum at a critical point C if f prime is less than 0 to the left and f prime is greater than 0 to the right of C. There is a local maximum at a critical point C if f prime is greater than 0 to the left and f prime is less than 0 to the right of C. So let me introduce you to my best friends in this situation. This first graph, this is our function. The second graph, which is the first derivative, is right here, and then our second derivative. All right, so our function is a cubic function. The derivative of a cubic function, of course, is a quadratic. And then, of course, the derivative of a quadratic is a linear. So this is going to be something x cubic, x squared, and x to the first. And so you can see by the power rule that that's how it works. And so if I'm looking at my function, I can see that on my function, I've got a maximum where f prime changes from greater than 0 to less than 0. So I've got a maximum where it is greater than 0 to the left and less than 0 to the right. And then I've got a minimum on my function right here where my f prime changes from less than 0 to the left and greater than 0 to the right. And what I usually do is kind of draw myself. I've got this, and we'll talk about this in just a minute, this point of inflection right here is going to line up with this minimum. So we'll say a point of inflection corresponds to where f prime changes from decreasing to increasing, also where f double prime changes from negative to positive, or vice versa. We'll talk about these three graphs a lot more in class. Determine the local extreme values of this function. All right, so here's our first example. Well, first thing I want to do is go ahead and find my derivative function. Y prime is equal to 8x cubed minus 8x. And then I will set that equal to 0. This will be my critical values. Factor out the common factor. All right, set each of these factors equal to 0. Maybe you recognize that this is the difference of squares, so it's going to be x plus 1, x minus 1. Or if we just set this factor equal to 0, we got to take the square root and the positive and the negative. So x squared is equal to 1, so x is equal to positive or negative 1. So now we're going to put these values on our number line, -1, 0, and +1. And then we need to test these intervals. And I always like to draw in my little test values. So I'm going to test a value to the left of -1, so -2, something between -1 and 0, between 0 and 1, and something greater than 1. And so pick the easiest values. And actually, it might be easier if we do write the two factors, x plus 1, x minus 1, because what we're going to do is we're going to plug each of these values into these factors and then determine the sign. So if I plug in a -2, that's going to make this first factor negative. That'll make this second factor negative, and that'll make, well, this third factor negative. So a negative times a negative times a negative is a negative. So in this interval, my function is decreasing. All right, so next I'm going to test my -1/2. Well, that'll make this first factor negative. That'll make this factor positive. -1/2 plus 1 is a +1/2, and it'll make this factor negative. So a negative times a positive times a negative is going to make this interval positive. All right, well, we'll just keep continuing. 1/2 is positive, and that's going to make negative. So that all is negative. And then if I plug in 2, positive, 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 that makes this all positive here. So what we can see is from this chart, I'm going from a negative to a positive. And so if you just think about your parabola, you're going from negative to a positive, we're going to have a local minimum. So we're going to have a local minimum at x is equal to -1, and you always have to give a reason, because f prime of x, or just f prime, changes from negative to positive. All right, so what else do we have? From here to here, we're going from positive to a negative. So we're going from a positive slope to a negative slope. And so what we've got here is a local max. And so we have a local max at x equals 0 because f prime changes from positive to negative. Continue, let's see, so we have the minimum here, we have a max here, and then we have a negative to positive again, so we have another minimum. And so I'm going to go ahead and just say comma and +1. I just added in my +1 here. All right, so now let's talk about the second derivative, and this is given, or it's called concavity. So if f prime, and if we think about our y is our position graph, our y prime is velocity. Y double prime is acceleration. So if y prime, this is my velocity, is increasing, which means the second derivative is greater than 0. So that means the slope of velocity is positive. Then y is concave up. Concave up looks like this. It's opening up. This is concave up. We use a sign chart with the second derivative to determine if and where y double prime is greater than 0. All right, so if y prime, the velocity, is decreasing, that means that y double prime is less than 0, or y double prime is negative, then y is concave down. And concave down looks something like this. This is concave down. All right, so what you'll have sometimes is you'll have a graph that's concave up, and then it switches over to concave down. This point right here, where it changes, that's our point of inflection, or our inflection point. And it says it is the point of inflection is the point where f double prime changes sign, or where f prime changes from increasing to decreasing, or decreasing to increasing. This is the point where the concavity of the graph changes from up to down, or down to up. Okay, so remember I was showing you my favorite, my little best friends in this unit, so I'm going to keep drawing those. Give me one sec. So we said this is like a cubic function, and notice I draw it kind of a little bit off. Here's my first derivative and my second derivative. And I label this f, f prime, f double prime. So where my function changes concavity, about right here, where it's going from concave down to concave up, this point, which is not the intercept, it's a little bit above, I'll identify it right here. That's my point of inflection. We can see that it lines up where f prime changes from decreasing to increasing, or vice versa, if our graphs were all negated, and then it also lines up where my second derivative changes from negative to positive. So if I can remember these three, I know all about this function. All right, so here's another example. It's not in our book. Find all points of inflection of the graph y equals e to the negative x squared. So if I'm looking for points of inflection, I'm looking for the second derivative, or the first derivative. I could actually use both, because according to my best friend, point of inflection right here is going to be where my first derivative goes from decreasing to increasing. So, yeah, let's try it. I'm actually going to work with the second derivative, though. All right, anyway. First derivative of this guy is equal to e to the negative x squared. All right, so e to the x is just e to the x, but it's times the derivative of the inside function. So this would be times, let's see, negative 2x. All right, and so I'm going to go ahead and just clean this up for my sake, for just ease of looking at this. All right, so there's my first derivative. My second derivative then, okay, so now I have the product rule. Here's the first function, here's the second function. So it's going to be first times derivative of the second plus the second times derivative of the first. Okay, let me clean this up real quick. So let's see, that's going to be positive 4x squared e to the negative x squared minus 2e to the negative x squared. Okay, so here's my y double prime. And so point of inflection, again, okay, I'm looking right down here. Point of inflection is where it changes from negative to positive. Okay, and sometimes I just draw my little graphs just to, off to the side. It's real fast. Cubic, quadratic, linear. All right, so I'm going to set this guy equal to 0. Okay, I have a common factor. Let's see, I can factor out a 2, and I can factor out an e to the negative x squared, right? So this is going to give me 2x squared minus 1. Okay, so with this being a base e, this is going to be positive all the time. So if I were to 2e to the negative x squared is equal to 0, e to the negative x squared is equal to 0. This is always going to be positive, so this can never equal 0. All right, so then this factor here, if I were to solve this, I would add 1, divide by 2, so x squared is equal to 1/2. Take the square root. Okay, so I'm going to have x is equal to positive or negative square root of 1/2. I'm just going to leave it like that. All right, so now let's put that on a number line. Negative square root of 1/2 and positive square root of 1/2. I don't know what this number is, but I'm going to pick some easy values. I know 0 is between that, and I know like negative 2 is less than that, and I know positive 2 is greater than that. And so let's plug it into our factors here. So this is always positive. So then let's just figure out, if I plugged in negative 2 here, negative 2 squared is a positive, times 2 is a bigger positive, minus 1 is going to give me a positive. So I don't really care what the actual number is. I just know that in this interval, it's positive. All right, if I plug in 0, that's going to make this 0 minus 1, which is negative. All right, and then if I plug in our positive 2, that's going to be a big positive, minus 1 is a positive. All right, so here is what I'm looking at. And this is my second derivative, and I can see that I'm going from positive to negative. So here is a point of inflection. And then again from negative to positive. So here's a point of inflection. All right, so let me show you this graph that I have. See if I can pull it up. Maybe. Oh, there we go. Okay, so right here is the negative square root of 1/2, and here is the positive square root of 1/2, and we can see that's where this goes from concave up to concave down, and then concave down to concave up. All right, number 2, the graph of the derivative of a function f on the interval is shown. On what intervals is f increasing? All right, so this is the derivative function. And it tells me to justify, so that is important. All right, so just give me one sec. Let me draw my friends. This is going to be cubic, quadratic. All right, so I'm looking at this guy. I'm looking at the first derivative. And on what intervals is f increasing? Well, the function is increasing. If we look at our function, we're increasing over here. That's where f prime is positive. We're decreasing right here, and that's where f prime is negative. And then we're increasing on the right side, and that again is where f prime is positive. So if you haven't kind of mastered that, use these little charts and they'll help you. So we're increasing where this function is above the x-axis, where it's positive. And so I can say it's positive between -4 and +1 because f prime is greater than 0. On what intervals is the graph concave up? All right, so concavity is, again, where concavity, if we are concave up right here on our function, that is where our first derivative is increasing. The slope is positive. So where this has a positive slope, so this part right in here is a positive slope. I'm going to just highlight it so because it's kind of hard to tell. This from about right here to, I'm going to say to the y-axis is increasing. And then we also have a piece that's down here that's increasing, positive slope. So I'm going to say from -2 to 0 union, and what would this other value be? 1, 2, 2.5 to 4. So about 2.5 to 4 because f prime is increasing. At which x-coordinate does f have a local extrema? Okay, so the local extrema is going to be where f prime changes signs. All right, so again, looking back to our function, see how we have a maximum here? And that's where f prime changes from positive to negative. We have a minimum right here. That's where f prime changes from negative to positive. And so if we're looking on this graph, we change from positive to negative right here at an x value of 1. We're not changing over here at -2. It equals 0, but it doesn't change signs. But it changes signs at an x value of 1. So at an x value at 1, so at x is equal to 1, we have a local, let's see, what would that be? If we're going from max, we're going from positive to negative slope, we're going from positive to negative slope. That is a local max. I'm always drawing these little parabolas because if I can see it, I can understand it. And that is because f prime of x changes from positive to negative. All right, and then question D, what are the x-coordinates of the inflection points of the graph? Okay, so an inflection point is where it's going to change concavity. So we have a concave down and a concave up, and if I'm looking at f prime, it's going to be where it goes from decreasing to increasing. So where we go from decreasing to increasing. So I'm going to say we have a decreasing slope on this left side, and then we're going increasing right here, so at an x value of 2, and then decreasing again, well, increasing to decreasing, and then decreasing to increasing. So we have 3 inflection points. So let's write those out. So at x is equal to -2, x is equal to 0, and x is equal to 2.5. And this is because f prime changes from increasing to decreasing or decreasing to increasing. All right, and then the last question for this problem says sketch a possible graph. So here's our derivative. All right, so let's just kind of take this apart. We know we have a 0 right here, and we have a 0 right here, and a 0 right here. So we know we're going to have some horizontal tangents. This is, if our derivative is positive, we know we're increasing. So I'm going to start by drawing, let's see. I'm going to be increasing and then flatten out. And then I'm still increasing and then flatten out. And then I'm decreasing and then flatten out. Something like this. It doesn't have to be perfect. But what I'm looking for is right here where we have a 0, it should be flat. And this should all be a little bit more increasing. I'm actually going to let's increasing, there we go. And you can erase that other line. All right, so this concludes part 1 of this section.